Have you ever noticed how your phone battery dies faster on a freezing winter day? Or wondered why electric car owners constantly complain about losing half their driving range when temperatures drop? What if I told you that your battery isn't malfunctioning in cold weather? It's actually obeying one of the universe's most fundamental laws with ruthless precision. Today, I'm going to reveal why winter weather becomes an energy thief that operates according to Emmy Noether's deepest insights about conservation and symmetry. The answer connects the chemical reactions in your car battery to the same thermodynamic principles that govern stars, and it will change how you think about energy storage forever. The mystery begins with a frustrating reality that every electric vehicle owner discovers during their first winter. You start your morning commute with a fully charged battery showing 300 miles of range, but by the time you arrive at work, you've lost far more energy than the distance should require. Your car's computer might show you've used 40% of your battery for a trip that should have consumed only 20%. It feels like the cold air is reaching into your battery and stealing energy directly. And in a very real sense, that's exactly what's happening. To understand this energy theft, we need to dive into the fundamental chemistry of how batteries work. Every battery, whether in your phone or your electric car, stores energy through chemical reactions. When you charge the battery, electrical energy is converted into chemical potential energy by forcing ions to move against their natural equilibrium. When you discharge the battery, those ions flow back to their preferred positions, releasing the stored energy as electricity. This process seems simple, but it's governed by the same conservation laws that Emmy Noether connected to the fundamental symmetries of physics. Emmy Noether's insights about energy conservation tell us that energy can never be created or destroyed. It can only change forms. In a battery, electrical energy becomes chemical energy during charging, then returns to electrical energy during discharge. But Noether's theorem also reveals something crucial about this process. It must obey the constraints imposed by the symmetries of the physical system. And one of the most important constraints comes from thermodynamics, the branch of physics that governs how energy flows in response to temperature differences. Here's where the cold weather becomes a ruthless energy thief. Chemical reactions inside batteries are fundamentally temperature-dependent processes. The ions that carry energy in your battery are molecules in motion, and their ability to move and react depends directly on their thermal energy, the random kinetic energy that comes from temperature. In warm weather, these ions have plenty of thermal energy, allowing them to move freely through the battery's electrolyte and participate efficiently in the chemical reactions that store and release electrical energy. But when temperatures drop, the thermal energy of these ions decreases proportionally. Cold ions move more slowly, react less efficiently, and resist the electrical forces trying to push them through the battery. It's like trying to pour honey in freezing weather. The cold makes everything thick, sluggish, and reluctant to flow. This isn't a design flaw in the battery. It's an unavoidable consequence of thermodynamic laws that govern all chemical processes in the universe. The energy loss occurs through multiple mechanisms, each obeying different aspects of conservation principles. First, the battery's internal resistance increases in cold weather because the sluggish ions create more opposition to electrical flow. When current encounters resistance, some electrical energy must be converted to heat according to Joule's law, a direct consequence of energy conservation. This wasted energy is lost forever to the environment, reducing the useful energy available to power your car. Second, cold weather reduces the battery's capacity, its ability to store energy in the first place. The chemical reactions that store energy during charging become less efficient at low temperatures, meaning the battery simply can't hold as much energy as it could in warm conditions. It's not that the energy disappears, rather the cold prevents the full chemical transformation that would store maximum energy in the first place. The battery reaches a chemical equilibrium that represents less stored energy than its warm weather maximum. Third, and perhaps most importantly, cold weather triggers additional energy demands that compete with driving the car. Electric vehicles must heat their passenger compartments, and unlike gasoline cars that can use waste heat from the engine, electric cars must generate heat using electrical energy from the same battery that powers the wheels. Heating systems, defrosters, heated seats, and even battery warming systems all consume significant power, directly reducing the energy available for propulsion. The battery warming systems reveal another layer of thermodynamic complexity. Many electric vehicles include heaters specifically designed to warm the battery pack to optimal operating temperature. These systems recognize that keeping the battery warm improves its efficiency enough to justify the energy cost of heating. It's like burning firewood to keep your firewood dry so it burns better. The physics of heat transfer makes this situation even more challenging. Heat flows naturally from warm objects to cold environments, according to the second law of thermodynamics. Your warm battery pack is constantly losing heat to the cold air around it, and maintaining its temperature requires continuous energy input to replace the heat that's constantly flowing away. The colder the ambient temperature, the faster the heat flows out of the battery, requiring more energy to maintain optimal temperature. Different battery chemistries respond to cold weather in different ways, each obeying the same fundamental thermodynamic principles, but with different specific behaviors. Lithium-ion batteries, used in most electric vehicles, suffer significant capacity loss below freezing because the lithium ions become less mobile in the cold electrolyte. Solid-state batteries, expected to become more common by 2026, may perform better in cold weather because their solid electrolytes are less affected by temperature changes. But no battery chemistry can completely escape the fundamental thermodynamic relationship between temperature and chemical reaction rates. The relationship between temperature and battery performance follows mathematical laws that connect to Emmy Noether's insights about symmetry and conservation. The Arrhenius equation describes how chemical reaction rates depend exponentially on temperature. A small decrease in temperature causes a large decrease in reaction efficiency. This exponential relationship means that battery performance doesn't decline gradually with cold weather. It drops off dramatically once temperatures fall below critical thresholds. Electric vehicle manufacturers have developed sophisticated thermal management systems to combat these thermodynamic challenges. These systems include heated battery packs, insulation, heat pumps, and even waste heat recovery from the electric motors and electronics. Each technology represents an engineering attempt to work with thermodynamic laws rather than fight against them. But every solution requires energy, creating the fundamental trade-off between maintaining battery performance and preserving driving range. The timing of energy loss also reveals important physics principles. Battery capacity loss happens immediately when temperatures drop, but the effects compound over time. A battery operating in cold weather for extended periods experiences more severe performance degradation than one exposed to brief cold snaps. This time dependency reflects the kinetics of chemical processes, the rate at which chemical equilibria shift in response to temperature changes. Preconditioning systems allow electric vehicle owners to prepare their cars while still plugged into charging stations, using grid electricity to warm the battery and passenger compartment before departure. This strategy recognizes that it's more efficient to use external energy to overcome thermodynamic challenges than to drain the battery fighting against cold weather physics during driving. The geographic implications of cold weather battery drain are substantial. Electric vehicle adoption rates correlate strongly with climate, partly because cold weather performance concerns affect consumer acceptance. Northern regions face greater challenges with electric vehicles not because of any technological inadequacy, but because of fundamental thermodynamic realities that no engineering solution can completely overcome. Future battery technologies aim to minimize temperature sensitivity through improved chemistry and design. Solid-state electrolytes, advanced thermal management, and new lithium-ion formulations all promise better cold weather performance. But each solution must still obey the fundamental constraints imposed by thermodynamics. The goal isn't to eliminate temperature effects that would violate physics, but to minimize them through clever engineering. The energy recovery during regenerative braking also changes in cold weather. Cold batteries are less efficient at accepting energy during braking, meaning less energy is recovered and more is lost as heat in the brake rotors. This represents another pathway through which cold weather reduces overall energy efficiency, demonstrating how thermodynamic effects cascade through interconnected systems. Even the aerodynamics of cold weather driving affect energy consumption. Cold air is denser than warm air, creating more aerodynamic drag that requires additional energy to overcome. The heating systems that keep windows clear and passengers comfortable also change airflow patterns around the vehicle, potentially increasing drag further. These effects combine with the direct battery performance impacts to create the comprehensive range reduction that electric vehicle owners experience. The relationship between cold weather battery performance extends beyond immediate performance impacts. Repeated exposure to cold temperatures can cause permanent changes in battery chemistry, reducing long-term capacity and lifespan. This reflects the irreversible nature of some thermodynamic processes. Energy conservation allows transformations between forms, but some changes cannot be undone without additional energy input. Understanding these thermodynamic realities helps electric vehicle owners adapt their behavior to work with physics rather than against it. Parking in heated garages, preconditioning vehicles while plugged in, and planning charging stops around cold weather performance all represent strategies that acknowledge thermodynamic constraints while maximizing practical utility. The broader implications of cold weather battery performance extend to grid-scale energy storage systems that use similar battery technologies. Wind and solar power generation often peaks during cold weather, but the batteries storing this energy for later use suffer the same temperature-related efficiency losses. This creates system-wide challenges for renewable energy deployment in cold climates. As electric vehicle adoption accelerates toward 2026 and beyond, cold weather performance will likely become an increasingly important factor in consumer decisions and technology development. But no amount of engineering innovation can completely eliminate the fundamental thermodynamic relationship between temperature and chemical processes. The laws of physics that Emmy Noether helped us understand ensure that cold weather will always present challenges for chemical energy storage systems. The next time you see your electric vehicle's range estimate drop on a cold morning, remember that you're not experiencing a malfunction. You're witnessing thermodynamics in action. Your cold air isn't just stealing your battery energy, it's enforcing the fundamental laws of conservation that govern all energy transformations in the universe. Your battery is obeying the same physical principles that control how stars burn, how refrigerators work, and how all chemical processes respond to temperature changes. The solution isn't to fight against these laws, but to understand them well enough to design systems and behaviors that work in harmony with the thermodynamic realities that Emmy Noether helped reveal. Winter weather reveals that even our most advanced technologies must bow to the fundamental physics that govern energy conservation and transformation throughout the cosmos.